Morning, everyone. Today, Richard Voyles is going to speak. Richard's a professor of robotics and Purdue Polytechnic Institute with expertise in electrical and mechanical engineering and computer science. His research interests include novel robotic mechanisms, sensors, self-adaptive software, real-time control, and gesture-based human-robot interaction. He served as the robotics guru at White House Office of Science and Technology Policy and was the founding program director of the multi-agency U.S. National Robotics Initiative. Today, he will present a talk titled Can Polymers Think? Embodied Intelligence in a Meta-Material World. Please take a moment to silence all electronic devices, but feel free to tweet using hashtag #DawnOrDoom. Thank you and enjoy.
All right, thank you. I guess I better silence my phone as well because wouldn't want to have that interfering with the talk. Well, thanks for coming. Great to see. It's nice to see a good crowd. Whoops, let me get the keyboard pulled out here. I'm definitely on the dawn side of AI and robotics, I'm going to talk a lot about a number of things here in what we call embodied intelligence. And I think robotics is really exciting. That even though there's been a lot of talk recently about the fear of robots and AI taking jobs, while it's true throughout history, technology has in fact displaced jobs, but almost without exception. The horseshoe is a classic example. Technology has actually produced far more jobs than it's taken away. Think of the blacksmith and the horseshoe, right? With the invention of the automobile, we thought, well, we didn't need horseshoes anymore. That course hasn't borne out. In fact, the blacksmith, who was a metal worker, was a very precious and rare commodity, actually, in communities and towns. What happened with the invention of the automobile was, suddenly we had millions of people working in the metalworking industry. And the idea of the horseshoe and the blacksmith really was democratized in a large way and produced a lot more jobs and a lot of suppliers who started working in aluminum and steel and metal forming of different types. And that's what I think is the future of robotics, because robotics has always fascinated us as humans because it's about, in some sense, ourselves. Aristotle, in fact, talked about this, back in 300 and so BC. I think this is something that is, and that's what's really unique. I think this is something that makes robotics really unique in that there aren't too many technologies we've been talking about for over 2,000 years. But you have to ask, and embodied intelligence, in fact, is one of those things. But how is it that Aristotle could have talked about robots? And in fact, he never used the word robot. The word didn't exist. Where did the word come from? Well, first off, who was Aristotle, right? So he was a Greek philosopher in early, almost 400 years BC. And he focused on logic, metaphysics, the theory of soul, though he had a very different definition of what soul is our kind of common definition today. And one of his famous quotes, I'm sure you've all heard of this, right, is attributed to Aristotle, that the whole is more than the sum of the parts. And that's really what embodied intelligence is about when we talk about robotics and AI. When I talk about embodied intelligence, it's the connection between what we commonly refer to, at least from a technology side, as artificial intelligence, and the mechanism that we call a robot, right? And we'll get back to this, what embodied intelligence really is about and what the implications are, but it's really about being more than the sum of the parts when we combine the two, even in biological creatures. The connection between our minds and bodies is actually critical to our intelligence, it's critical to our development, it's critical to what we often call the soul, and it's really exciting. But of course, the question is, if he never used the word robot, well, where does that word come from? There was a Czech author by the name of Karel Čapek who in 1921 created a play called Rossum's Universal Robots. And this is the first use of the word robot that we know of. It was derived from this Czech word robota, which means work, or in this case, forced work. Anyone guess what the theme of this movie might have been in 1921? Yes, the takeover and demise of humanity due to the robots, right? This is why it's so fascinating to us as humans. Because when we talk, and why Aristotle studied it, right, and talked about it, is it's, in some sense, it's the replication of humans. It's from both an AI perspective, meaning the mind perspective, and the physical perspective, the body. And so philosophers have long pondered this, right, of, well, what happens if we can create not biological selves, but mechanical selves? And those are some of the things that Aristotle was talking about, even though he didn't use the word robot. And of course, this word robot long presages the actual mechanical robots that appeared really not until the late 1950s. And so it's been really, for generations, right, even without having an example, you know, we've been talking about that philosophical conundrum, right, which is, well, gee, are the robots going to be evil? Since this is about fiction, I'm going to take a little bit of a digression here, because I love science fiction. And I grew up in the era of the original Star Trek with William Shatner, you know, and the hokey kind of monsters and plot lines, for, of course, he always saves the day. But science fiction is neat, right? I like science fiction because it deals with these, not just the the technology that we kind of want to see, and science fiction has predicted, in many cases, interesting technologies, but also this ponderance of the human condition, if you will. And of course, 2001: A Space Odyssey, right, just blew me away as a kid. And this, of course, was really a radical departure in sci-fi, right, because of the realism. But also, it's really kind of a mind-bending movie. And what does it include? HAL, the classic evil AI, right? And this was such a great representation. This was HAL, or at least what we would now call the GUI of HAL, or the graphical user interface. But it was just a cold kind of observing, almost Orwellian kind of presence. And what was interesting about HAL was, HAL was just trying to preserve the mission, and the humans got in the way, or so HAL perceived. But there have been lots, again, of references in science fiction. One of the first movies, right, Metropolis, had robots in it in 1926. I want to point out, by the way, while I'm talking about movies, again, the technology, did movies replace theater? No, right? We still have theater. More importantly, movies was a technology that really brought theater and performances to the masses, because suddenly, right, with the invention of film, we could now distribute a single performance all over the country and all over, so that lots of people could see it for much cheaper than going to the theater. And it hasn't destroyed actors in any way. In fact, it is the whole entertainment through theater, through performance art, has just blown up, right, worldwide. Because not only do we have lots of actors who are still acting in movies, right, but we have editing, we have the editing jobs that come with that, we have special effects teams. I mean, George Lucas and the whole Industrial Light and Magic, which brought us lovable robots like C-3PO and R2-D2. These have just exploded in terms of providing more and more jobs through the technology of, again, movies. Much like, the invention of the automobile actually created a great more jobs. Now this was about evil humans and good humans, right? And these were mostly good robots. That has not always been the case. And in fact, right, we've seen lots of examples of both good and bad. Again, in my era, the Terminator sequence with Arnold Schwarzenegger, I mean, that really was an important movie, especially for roboticists. Because when I talk about science fiction, I don't just look at it as entertainment, right? I actually draw inspiration from some of the ideas that are presented. Because again, a lot of the things that we want to have, yeah, there's the standing joke about we still don't have our flying cars yet, right? And flying cars have been predicted in movies for decades. But many of the neat things in technology appear first in science fiction, right? Because A, it's easier. Question?
I want to give a shout out to the film Ex Machina.
Ah.
I originally stayed away from the film because I thought it was a sci-fi horror film. But if you look a little bit beyond that,
Oh, yeah.
it's an ontological and epistemological look at AI and the terms that it is fascinating.
It is indeed. If you're not familiar with Ex Machina, you should look it up. Ironically, the Latin title, speaking of Greek philosophers. Yeah, it's a really cool and a very philosophical movie. And yeah, it's one of those movies you can watch and rewatch because of all the things it explores, right, in robots as our collaborators, co-robots, and, the theory of potential nemesis. But, right, the ultimate nemesis was not the first Terminator, but Liquid Metal Man from Terminator 2. So if you haven't seen Terminator 2 and Liquid Metal Man, this is a short clip from the movie. And Liquid Metal Man is just that. Here's Liquid Metal Man pouring into an elevator after stabbing his way through, and then reforms himself into, of course, anything he comes in contact with and can replicate the form of that thing. And of course, he's made of this liquid titanium alloy, which flows and does and can do all these amazing things. But here's what I looked at when I saw this. Right here, okay? That liquid is computing while it's pouring itself through the surface. Okay? It's thinking, okay? Oops, we've already kind of talked about that. The point is, right, in order for this thing to be maintaining its shape, to be changing its shape, right, it has to be computing. There's all kinds of AI going on. But we have a problem here, is our computers are entirely based on positional certainty. And there's none of that in a liquid. Okay, hold that thought. So, one of the things I do, whoops, let me get the other video started, is emergency response robots. And these are some of the mechanisms we work with and that do all kinds of cool things. This is like a 2D treadmill that's actually a serpentine snake and all kinds of things. I'm not going to talk about the details of the technology. But, the bottom line is I've worked, not only, as mentioned, I've had a lot of fun since leaving Purdue as a bachelor student. And then circling back and coming back to Purdue, it's been really exciting. And the opportunities I had to do stuff like this that Purdue as an undergraduate introduced me to, I think is phenomenal. Again, eventually working at the White House as the robotics guru, right, where we talked about things like Fukushima incident and how we can develop robots to get into, situations like this. Now, unfortunately, this is a scene from the aftermath of the earthquake and tsunami that hit Japan in 2011. And this is a really chaotic scene, even for humans to really comprehend and understand, right? And part of the problem is we're used to these kinds of structures. And we use those a lot in our everyday life of engineered structures that, okay, walls are vertical, floors are horizontal, so are ceilings. Cars don't generally sit down here in this trench, and there are lots of problems with just walking around these areas, both for for humans, even for dogs and animals. We use search animals often in environments like this. Of course, these kinds of things happen all the time across the world. It's not just Fukushima was bad because it was a double whammy, right? We had big earthquake and then followed by an enormous tsunami. And that, of course, is what took out Fukushima, is our technology, right, was designed for single point failure. And the nuclear power plant at Fukushima was, power went down when the earthquake hit. So we lost power. Okay, no problem. The systems are designed for that. They automatically went into a shutdown mode so that the reactors had shut down. And we're in this safe position, so the control rods were put in to stop the reaction. But of course, the reactor vessels are still extremely hot. They don't just cool down immediately, even though they've stopped the generation of power. And so what happened was, and they were at that point relying on backup power because the whole power grid had gone down. It was a massive earthquake. And so backup generators were keeping things running, particularly the pumps. Now the problem is, it was a US design from GE that we normally put our nuclear reactors on rivers. You don't have to worry about tsunamis. All the backup generators were located in the basement. The Japanese engineers said, wait a minute, this might be a problem. All ours are on the coast. What if there's a tsunami? And they're like, oh, well, let's just duplicate the design. In case you don't remember, there are actually two Fukushima plants. There's Daiichi and Daini, and they're sister plants just a few kilometers apart. When the tsunami then hit, it overran both plants, flooded the basements, and killed the generators at Fukushima Daiichi. And that's where all the problems were. On Daini, it was about 3 or 4 meters higher, and one of the generators survived, and they were able to keep the power plants in Fukushima Daini operating, so the pumps were cooling the system and the whole bit. But that's what happened when the power went out. We lost control, couldn't tell what was going on inside the plant, and of course couldn't keep things cool. And so bad things happened. But we use robots a lot for things like that to help because the problem is now you don't want to send necessarily humans into that environment because now you have while Daini was perfectly safe, Fukushima Daiichi then eventually had a hydrogen gas explosion and near complete meltdown of the internal core, and that can release actual radiation, which is dangerous for humans. So imagine, whoops, I went one too far. Imagine Liquid Metal Man as a good robot, okay? I'm building these little soda can-sized robots that are supposed to crawl through the environment, right, and uncertain environments, but it takes a long time for a small robot to crawl around. So that's what the bigger robot was to carry the smaller robot kind of in marsupial style, but the big robot can't get down into the rubble. Imagine Liquid Metal Man. Okay, we could just pour good robot, right, good metal, down into the rubble that we saw here in any of these cases. It would then go down and reassemble itself and kind of slither around like a snake or whatever, maybe expanding itself to push up debris and help in those critical 36 to 48 hours when we really want to find, it's a really critical time window when we need to find potential survivors of these kind of incidents in order to save them. And so that's what we're trying to do with robotics and AI now. So man, if I could have liquid metal man, that would make my work really great, okay? But there's that problem I mentioned of positional certainty. And what I mean by that is all of our computing today with this von Neumann kind of architecture, which is the idea that we can have a super fast processor executing one instruction at a time. But if we run those really fast, then we can have really high performance computation going on. But here's the problem, right, is everything is based on lithography, which determines the outline of our transistors, because our computation for a microprocessor is based by transistors. Our memory for our microprocessor is based on transistors. And all those require very precise positioning in order to operate properly. So, gosh, if they were made of liquid metal, even, okay, semiconductors are not conductors like metal, but we're going to assume in sci-fi they can be, liquid metal man is also a liquid metal semiconductor. But when you're pouring, you're deliberately completely changing your form. Liquids, right, what differentiates a liquid from a solid is whether they're basically something like a crystal lattice. Doesn't have to be crystalline, but if there's a lattice of molecules where the molecules stay in positionally specified region or areas, right? They don't move very much. Whereas liquids, the molecules don't float around like a gas, but still they're constantly moving around inside the fluid. We don't know how to build computers that way, right? Because everything we've done with this von Neumann approach has been, based on these things, okay? In fact, we do have some theorized ways. Quantum computing makes use of what we call entanglement, which doesn't require positional certainty. In other words, we can have effects between two things that are arbitrarily positioned if they happen to be entangled. We don't understand this very well. We do have some very primitive quantum computers. But an interesting thing is, some people have theorized that biological structures do quantum computing as well. I'm not sure I believe this paper that says homing pigeons. We don't fully understand how homing pigeons work in terms of how they remember, how they get back to where they came from. They've put magnetic hats. We know they're not just using a compass. That would be way too inaccurate anyway. And we don't fully understand how homing pigeons actually home. But there was a credible article, scientific article, that claimed it could be through quantum means. I kind of doubt it. There isn't enough evidence yet. But maybe as we develop our quantum computing, right, we could have liquids that think. But for now, I'm going to assume that flexible polymers are good enough. And that's why the title of my presentation, can polymers think? The history of polymers is interesting because it's recent. What we did with polymers were invented just before World War II. They've been around for about 80 years, and they've really revolutionized the things we can create with our manufactured devices, because in this space of the materials we had accessible to us to make things, right, from the dawn of man, right, dawn of humanity, I should say, wood and paper, and we went through, of course, the Bronze Age and the Iron Age of discovering, resources the Earth had And in many cases, with the Bronze Age and the Iron Age, bronze is not something we found in nature generally. We created that through alloys, right, of copper and often tin or arsenic. And so we modified this charts like this. And what this chart is it's a map of one particular physical constant with another, right? When one is Young's modulus, that's kind of how stiff things are, and this is its density, how heavy things are. And what was cool about polymers is they came in and filled a gap, not just in density and Young's modulus, but in conductivity and numerous other things that we didn't have good materials for. And yet these are things that we synthesized in the lab and gave us things like rubber, like polyethylene, like all kinds of thermoformed plastic that gave us McDonald's toys and the Great Pacific Garbage Patch, right? So again, with any technology, there are good and there are bad. But while it filled a gap in the materials we had, it didn't really change the way we did design or that we did manufacturing. It just gave us some new materials that we could use with certain mix of properties. What we want to do when we talk about smart materials and whether polymers can think is, what if we actually, instead of just adding stuff to this existing space, what if we expanded the space? Added new dimensions that we traditionally haven't had before, not just density and Young's modulus and thermal conductivity and electrical conductivity, but the ability to sense, the ability to think, compute, the ability to act. Those are what we mean by what we call designer polymers, is polymers that can actually embody not just the form of something, but the function as well. And that's what we set out to do, to kind of answer this question. And there are some important reasons for doing this. The evolution of computing, technically, this is electronic computing. We actually had mechanical tabulators way back, another 50, 100 years earlier. Of course, we had the abacus in ancient times. But this has been the history of modern computing. From the ENIAC to, the iPhone 10, or X, however you want to call it. But here's something interesting. We've kind of devolved a little bit, because notice that went from this room-sized thing that really couldn't do very much to, PC, which kind of wasn't predicted by science fiction, And then the phone, which is a super fast, brilliant computer, right? It's got a great user interface and everything, getting smaller and smaller and more embedded. Watson, which, was famously beat Ken Jennings, the reigning Jeopardy champion way back in 2011-ish, looks a heck of a lot more like that than it does look like a cell phone, right? So when we try to do things like humans do, even though, with a whole lot of people and a whole lot of programming and a whole lot of money, Watson was able to defeat a couple of Jeopardy champions. If we look carefully at this, Watson consumed 80 kilowatts and weighed 5.4 tons. This thing, right, 20 watts, about the weight of a laptop, and have we really evolved? Because Watson could do something we intrinsically think of as being very human, right? This ability to interpret trivia. Yet, really couldn't generalize outside. I couldn't drive a car, okay? And IBM now is taking Watson, taking the AI engine, and using that for medical diagnoses, which are great. But they have to do a complete retraining, okay, on a completely different data set, depends on how what you show them and everything. There, of course, have been recent reports about the risk of racism in AI, right? Where depending on what you show the robots or the AI engine, and again, it's not really generalizing like we do as humans. And this is why I'm not too worried about at least the near future of AI, replacing humans, is because that ability to generalize is not really there. But again, this power consumption is enormous. That's the biggest thing that's limiting Moore's law, which shows the expansion of computing and compute power inside silicon circuits, because we just can't get the heat out of there anymore. We're literally running into a cooling problem, where biology solved this thousands of years ago, right? And so what is it that biology does different? This is Mike, a headless chicken. And yes, Mike survived for 4 years in Colorado, Fruta, if anyone has been there before. It's a great biking mecca, without a head, okay? And the reason is because one of the things biology does is distributes computation throughout the body. Again, there's this close connection between body and mind for biological creatures that we haven't really been able to capture to the same degree. And the fact that this body, which again, we go back to Aristotle's comment on more than the sum of the parts, the mind is gone, theoretically, okay? But a large part of the computation and the thinking that goes on kept Mike on going for 4 years. And so we've been working a lot with artificial neural networks for decades. That too is one of the key technologies, right? And the question is, what is that? What is the essence of when we talk about a neural network? And these basically are the structures in our bodies, in our brains, but they're not entirely in our brains because they are distributed throughout our bodies, which basically manage those three things that we want to add to polymers, right? The ability to sense, the ability to compute, the ability to actuate. And the way these networks work is there are lots of synapses. We've heard about those things. They make the interconnections between all these neurons, which make up our brains and our entire nervous system. And then the synapses are represented. This is an artist rendering, but the synapses represent connections between the neurons. The neurons represent very simple computations, and they're often analogous to the single instruction in a computer program. But in here, there are billions of them. And the difference is they work in parallel, right, rather than one at a time, like our computers. Okay? And that is a critical problem, because that's what ends up. We have to make these structures faster and faster and faster so they can now do billions of instructions per second. Billions. And many of us have trouble with thousands or hundreds of thousands, right? When we try to contemplate what does that mean. But now our computers are doing billions of computations a second with billions of pieces of information, memory. And so the basic model, and this is a simplified model because biological neurons are very complex. But in the field of artificial neural networks, we've been using this basic model, which is there's a soma, and these are biological terms we've co-opted into a technology that represent our synapses, the soma, and this interconnection, and the massive interconnection is what's really important, getting back to that embodied intelligence, the mind-body connection, is what drives a lot of the actual physical creation and deletion, mostly deletion of these synapses or connections. Where signals come in, either from sensors or more likely just because of the billions of neurons we have, they're coming in from other neurons. all these things are converging, much like an interstate where you get this behavior emerges from the sum of the parts. And in our simplified computer science view of a biological neuron, we have an artificial neuron, which really comes down to a few things. And this is based actually on the work of one of my former students who's here in the audience today, Robert Naraki. But the bottom line is that the soma manages summing all those pieces of information together and then coming out with a single output. Okay? Much like we do when we're trying to decide on our vote, right? If you have one vote to cast, right, you take a whole bunch of pieces of information, you sift through, you weight things differently, and then you sum them all together and come up with an answer, right? And so we have to do the same thing. We have to have weights, and we have to multiply the weights times the information input, right? And this is part of our fusion of information. And then we're going to sum them all together and come up with something that says, yeah, okay, which way am I going to vote? And these are the parts of this basic simple equation that goes through those pieces. And there are some particularly hard parts. It turns out that summing in an electrical circuit is easy to do. Very, very easy. You don't even need a transistor for that, although in computer science we use transistors for everything. In electrical engineering, we can get away without it. Also, weighting, multiplying is relatively easy and is very closely tied to how we add or sum. So the hard parts are memory and this activation function. And since I'm running out of time, I'm going to skip over this a little bit, but just to say that what we developed and was a major part of Robert's thesis actually was this idea of what's called a memoristive device, which allows us to combine the memory function and the multiplication into a single simple polymer device, not a silicon device, but something we can make with polymers and in fact print. And that gives us what's akin to a biological edge. If we can print things out of a really cheap material, as opposed to in our semiconductor processing, we used very expensive processes in a clean room on very expensive material, silicon, right? And then we make chips, which are pretty expensive. I mean, we're talking hundreds of dollars just for an Intel chip or something, a large chip. Whereas, man, if we can just print some cheap polymers, we don't need a clean room, we'll be able to make these by the billions, okay? And again, that's what this device allowed us to do, was take those two really, one of those difficult, one easy problem, one hard problem, combine them into a single device that gave us the ability to do programming and execution. And the other thing we did, I'm going to skip over that also, was we created an activation function, which is that method of deciding, okay, once you have all these pieces of information and you've mixed them together, how do you actually decide you're going to vote one way or the other? And so this has created our basic building block for an entire neuron. And I'm going to show you a quick video on that some of this work that resulted from a big group here at Purdue. It includes Robert, includes a number of other faculty members, a total of 8 faculty members working on what we call form plus function 4D printing, because it's normal 3D printing in the sense that we're printing the structure with polymers, but we're adding sensors, computation, and actuation basically throughout the material to make maybe not a liquid metal man, but a liquid chicken man, okay? So it's a kind of a polymer that bends in soft robotics. Let me show you this video. And because this is the idea. We started off with a 2D structure, so we've made 2D polymers that we're using 3D printing techniques then to augment so that inside the layers, we're printing these neurons. And then this is actually a lithography fabricated, and this is our first example we call nucleus, which is like does basically what with just, in this case, it's a single neuron because all it does is run away from the light, but it scurries away from light. Now, that's very simple. We could make that in a number of different ways. With modern CPUs, the bottom line is there is no modern CPU included in this. This is entirely a polymer brain that then we've printed and fold up into a structure to provide the actuator. We added a motor on the outside because we used what we see on the outside is just some gears and stuff to give us the actuation, but the sensing and computation is all based on these polymer electronics. Okay. We've also been working on smart Tupperware as part of this also, because our goal is to take ordinary plastic devices, right, and imbue them with their own intelligence to make everyday convenience, to try to improve convenience and usability for things in what we call what's been commonly referred to as the Internet of Things. Because as we went to the information age, right, the Internet connected basically people with information. Now we have the ability to connect things to the Internet as well. And so the question is, how do we make that actually useful for the human users of the Internet? I'm going to stop there by saying, in closing, what this really is about when we talk about the Internet of Things, when we talk about embodied intelligence, there was a recent article by one of my colleagues entitled, Will the Future of Robotics be bodies with brains or brains with bodies? And this is an area that philosophically we don't understand much of. I'll give a quick example of cerebral palsy. This is a debilitating disease that affects kids and usually ends up in neurological impairments that last for a child's lifetime into adulthood and can be, again, very debilitating in their adult life. The interesting thing about cerebral palsy is, from a disease standpoint, it's very short-lived, and it disappears by the time a child is about 3 or 4. And in fact, all effects, medical effects of the disease completely, in other words, the child completely recovers from it. The problem with cerebral palsy is it affects that period of time from basically 1.5 years to 3, where if it sets in, that's exactly when, and that's a very critical time for the development of the human brain. All cerebral palsy does is it turns off temporarily turns off some of the communication that goes to the motor cortex. And so it's just at a very critical time that they lose the ability to do the kind of things that kids do, right? Infants do this all the time, and it's very important to their long-term development. Children, right about that time, they're starting to walk. They've gotten out of the crawling stage, usually by the time cerebral palsy sets in, but they're really getting to the point where they can explore the world and understand the world, and they're building those synapses between their neurons, right? Mostly paring down ones that resulted from birth and developed in the early first year and a half. Now they're paring them down to really understand the world in a connection between the mind and the body. But then a lot of those learning opportunities are never replicated later in life. And that's why cerebral palsy is so damaging, is because the child can never relearn physiologically those things that they needed to learn. And that's just one example of this difficult connection between mind and body that we're going to try to explore in the area of what we call co-design in products and smart products, of how you can build a cell phone where you evolve both the software and the hardware simultaneously, for example. And with that, I've run my limit, and I really appreciate you coming and listening to me go on, and I'm welcome. I guess we are in a transition period. I'm happy to stay here if anyone wants to for a few minutes and talk informally and take questions, but I appreciate thank you for your time.